Welcome back, pre-calc students. We are moving forward into Appendix A.4, looking at rational expressions. This Part 1 video will cover the first 6 examples, and there's also a Part 2 video that will cover the last 2 examples, examples 7 and 8. The focus of Appendix A4 is our essential question: how do you go about finding the domain of an expression, which we don't have a whole lot of experience with. We have a little, but we're going to also work with what we call interval notation. We'll get you familiar or more familiar with that. And what is the process for simplifying all of these rational expressions? So let's see what we can do here. Moving forward, domain of an algebraic expression is really the set of all real numbers for which an algebraic expression is defined. That represents the domain of the expression. So what x values can you actually plug in? Well, I really like how we start out in example 1, part A. What's the domain of the polynomial 2x cubed plus 3x plus 4? I want to know what numbers, negative, positive, zero, fractions, decimals, irrational, whatever you want to come up with, what numbers can you actually plug in for x within that polynomial? Well, they gave us a huge hint by calling it a polynomial, because if you're thinking about what numbers can be plugged in for x, you shouldn't be able to come up with anything that you cannot use. Polynomials allow you to use all real numbers. So we're going to make a note along the side. All real numbers is the domain for every polynomial. Okay, so you can say that the domain is all real numbers. Now that's great in words, but I want you to become very familiar with interval notation. And interval notation is using parentheses and square brackets along with real numbers or infinity and negative infinity symbols to represent something like all real numbers. Well, the interval notation that represents all real numbers is a parenthesis that comes before negative infinity, comma, infinity followed by a parenthesis after the infinity. That's what represents all real numbers in interval notation. So something we're going to get used to. This is really the way I want you to write the answer. So the more familiar we get with that, the more I expect that out of you, okay? Now, part B, completely different problem. It's a radical expression. You see the square root. We know if we stay within the real numbers, which we are here, you cannot have a negative value underneath the square root symbol. It's okay to have 0. It's okay to have any positive number, even something like positive 2. You can take the square root of positive 2. You may not end up with a rational answer, but you can come up with a real number, an irrational number. There's nothing wrong with irrational. You just can't let the quantity that's underneath the square root be negative. So you need to make sure, we'll make a side note here, make sure the expression under the radical isn't negative. Okay, so if it's not going to be negative, I need to make sure that x minus 2 is greater than or equal to 0. Right? So that I can let it be 0, I can let it be anything positive, I just can't let it be negative. One quick step of adding on 2 actually allows you to come up with the domain. That's it. Right there, you can say that whoops, let's try that again. That is the domain, all x values, all real numbers greater than or equal to 2. Now, there's interval notation for that as well. So think on a number line that what that means is that here, this is your 2. You've got a solid dot, and you're shading and including everything off to the right. And if I'm going to put that in interval notation, the way I really, really, really want you to put your final answer, you always in interval notation work from small to large. That's why negative infinity came before infinity. So if I'm working from left to right on the number line, 2 is my starting point, and I get to use it. Because your starting point is a number you get to use, you put a square bracket there. I had parentheses up above by negative infinity, infinity, because those are directions that you're going. It's not a specific number that you actually get to use. Now, where am I stopping on the right-hand side? How far do I get to go to the right? I'm not stopping anywhere. I'm heading in the direction of infinity as far as I can go in the positive direction. You always have a parenthesis after infinity. So again, this is what I want you to try to get used to. Nice job with the second one. Okay, the third one. I honestly think these are some of the hardest problems to be working with. So let's see if we can tackle the third one. Okay, so in the third one, we have a rational expression, a numerator and denominator. It's in the form of a fraction. And when you look at the domain of something for a rational expression, there's one number that you can't divide by. You can't divide by 0. So you can plug any number you want in for x in the numerator. X plus 2 is a nice polynomial. Any number is going to work up there, and any number really will work with x minus 3 in the denominator. But the problem is, because it's in the denominator, you can't let it equal 0. So a little side note, make sure that the denominator isn't equal to 0. Okay, so here's my quick work. What if it is equal to 0? Set it equal to 0. Solve it for x. That is the one number that will cause the denominator to equal 0. We cannot use it. So if you're looking for a domain, you could write it like this. X cannot equal 3. All real numbers except for 3. But again, you could come up with an interval notation. If I show you what it looks like on a number line, that I can use everything except for 3, it means you'd have an open dot at 3 because you can't use it. And you'd shade everything to the left and everything to the right. And I want to come up with the interval notation that represents this. And what that looks like is there's actually 2 separate parts to the interval notation. You're going to start with as far as you can go to the left. If there's no stopping going off to the left, then you're heading in the direction of negative infinity. But there's a stopping point because you can't use the 3. So the first stopping point, the one stopping point for the first interval of numbers, and since you're not using it, you have to put a parenthesis after. If you put a bracket after it, it means that you get to use the 3 and that we know that you can't use it. That should be all the numbers less than 3. Union, put a big U in between. It means union, which means or. And now I want all numbers greater than 3. So I can't use the 3. You got to use that as your starting point. You're not using it though. You're working with numbers that are greater than 3. You can't actually apply the 3. And as far as you can go to the right, and you never get to include infinity. So you always need the parenthesis there. So this is what we're working towards. Takes a while. I know it takes practice. Be patient with yourself, okay? Honestly, that might have been the hardest process that we need to cover. So let's see if we can keep tackling. If you need to relook at these examples at a later time, great idea. I know those types of problems are going to show up on the test. Simplifying rational expressions. This is what we're going to tackle for the rest of the examples that we cover. So some helpful terminology that we can be aware of. The quotient of two algebraic expressions is a fractional expression, and the quotient of two polynomials is a rational expression. So we're going to be specifically working with the rational expressions. A fraction is in simplest form when its numerator and denominator contain no common factors. So we're going to have to do some factoring like we did in Appendix A.4. When simplifying rational expressions, make sure to factor each polynomial completely to determine whether the numerator and denominator have factors in common. So we got to look for some common factors. So we're going to take a look at example 2 and example 3. Both of them ask us to do some simplifying. So when I start in example 2, I know I have a trinomial up in the numerator. I'm going to see if I can break that down into two binomial factors. The x squared as my first term will break down into x and x. I'm coming up with two numbers I multiply to get -12 and add to get a 4. Ooh, one's going to have to be positive, one's going to have to be negative. The larger one's going to be positive. How about positive 6 and -2? There's our numerator factor. They multiply 6 and -2 to give me -12. They add to give me a positive 4. The denominator has two terms. I look at those two terms, I see a GCF. You look and see if you can find a GCF. Pull out that GCF of 3. And when you divide both terms by 3, you should be left with x minus 2. You can redistribute the 3. It brings you back to, should bring you back to the 3x minus 6. My one quick step of simplifying, look for something in common. Both top and bottom, numerator and denominator, have that x minus 2. There's an x plus 6 left up on top, a 3 left down below. It may be tempting to simplify the 6 and the 3, but the 6 is a term, the 3 is a factor. You can't cancel out a term and a factor. You have to pull out the factors. It's the factors that are in common, not terms. So be careful. Do not try to simplify that anymore. This is beautiful for a final answer. Okay, we can keep moving. We can do this. So moving forward to example 3, the first thing I recognize in example 3 is that the terms in the numerator are not in a great order. It's not in standard form. It's in ascending order versus descending order. So I'm going to rewrite just above it, -x squared plus x plus 12. And my very first step of factoring the numerator, I'm going to factor out a -1. That'll change all the terms' signs. X squared minus x minus 12. The denominator, I want there to be a GCF, but there isn't. So my whole process here, I'm going to start the process in my very first step. I'm going to do my slip and slide method. So I'm moving the 2 over, so we get x squared minus 9x plus 8. Remember, the 2 gets multiplied by the 4 in the first step. We won't forget about that 2 because we'll come back. Okay, the numerator. Don't lose that -1. I'm trying to come up with two numbers I multiply to get -12 and add to get a -1. I know that one of them is going to be positive, one's going to be negative, and the larger one's going to be negative. How about -4 and positive 3? And x and x are going to be used for my first terms to get my x squared. Down below, I can start out with the x and the x to get the x squared, multiply to get 8, and add to get a -9. Ooh, two negative numbers. How about -8 and -1? Be careful. Remember that leading coefficient was a 2, so we have to take the 8 and the 1 and divide them both by 2 and try to simplify. So I'm going to bump up a little bit more. I'm leaving the numerator as it is. I can simplify in this next step. Down below, 8 over 2 simplifies down to a 4, so x minus 4. But 1 over 2 doesn't simplify, so that forces that 2 to go in front of the x, so 2x minus 1. That should be our factored form using the slip and slide method for the denominator. Only thing that I see in common that I can pull out is the factor x minus 4, so let's get rid of those. What I'm left with, I don't need to redistribute the -1. Leave it as a -1 out in front of x plus 3. Leave 2x minus 1 in the denominator. That doesn't have to be in parentheses down in the denominator because there's nothing else there. Check off example 3. Nice job with that. Okay, our next slide. When we look at the next slide, it's just full of patterns. It's patterns that you need to be aware of. If you want to be able to do operations with fractions, make sure that you have common denominators, whether you're adding or subtracting. You do not, I repeat, do not need common denominators if you multiply or divide. You always have to change dividing of fractions into a multiplication problem. So use these processes to help you out. If it's just too many variables and it just seems, oh my gosh, that's overwhelming, I can't follow what they're talking about, the good news is we've got more examples, and the additional examples that you'll see here, this is the last slide that I'll cover in this video. These additional examples will help you to actually apply some of those processes from that slide, the slide that we just went through. Okay, so example 4, multiplying rational expressions. So, there's a lot of polynomials that I see going on in those rational expressions, and what I need to be able to do is a whole bunch of factoring. So I look at the first numerator, and I will do the slip and slide method. I'm just going to do the slip and slide method a little bit off to the side here. I know I'm going to take the 2 and multiply it by the -6. So I'm working with x squared plus x minus 12. That breaks down into, we factored something like this already. Multiply, get -12, add to get a 1. How about a positive 4 and a -3? So x plus 4, x minus 3. And because that leading coefficient was a 2, then by the slip and slide method, you have to go back and divide each of those factors by a 2. So what happens here, 4 does divide by 2 to give us 2. 3 doesn't divide by 2, so we got to put the 2 out in front of the x, and that should be the factored form for the first numerator. So start out with x plus 2 multiplied by 2x minus 3. If you don't like my slip and slide method, if you have another method that you can work with, that's absolutely fine. Guess and check or AC split, those are all good methods. I'm going to move down to the first denominator. X squared plus 4x minus 5. Two numbers I multiply to get -5 and add to get a 4. How about a positive 5 and a -1? Okay, halfway through, we can do this. X cubed minus 3x squared plus 2x. There is a GCF of an x that I should be pulling out. Maybe I can do this work right here. So if at least I pull out an x to begin with, that decreases every x power by 1 power. So I should be left with x squared minus 3x plus 2. Don't lose that x, but the trinomial that's left inside parentheses, two numbers I multiply to get 2 and add to get a -3. How about -2 and -1? And finally, in that last denominator, 4x squared minus 6x, I bet we can pull out a GCF as a first step, and that's probably all we're going to be able to do. Between 4 and 6, you can yank out a 2. Between x squared and x, the lowest power is x to the first. So if you pull out a 2x, 2x times 2x brings you back to 4x squared. Carry my minus sign. And 2x times 3 brings me back to 6x. Okay, voila. Now you get to cancel like crazy. At least you hope you get to cancel like crazy. So one thing I see between the top and the bottom, you can cancel them out in any order you want, but I see an x minus 1 in common between the numerator and denominator. I see a 2x minus 3 in common between the numerator and denominator. and I see a power of x out in front there that's in common between the numerator and denominator. Voila, it looks a lot better now. What's left up in the numerator, you don't need to multiply back together. Leave it in factored form. X plus 2, x minus 2. Down in the denominator, since there's a 2 and a factor x plus 5 left, let's put the 2 in front of the x plus 5. Don't try to cancel the 2 in the denominator with the 2 in any one of those factors up in the numerator. You can't do that. Doesn't work. Please don't over cancel. That is as pretty as you can make the final answer in example 4. Okay, we're down to 2. We can do this, guys. Okay, ooh, we have some sum and difference of cubes to work with in example 5. And in the process of doing that, we also have a division problem. So be cautious with how we do example 5. So remember how we work with cubed roots, cubed roots, cubed roots, cubed roots. Okay, so x cubed minus 8. Let's see if we can do the factoring here. X cubed minus 8, the cubed root of x cubed is x. The cubed root of 8 is 2, so keep the minus sign in between. The trinomial starts out with the square of x, minus changes to plus, multiply x and 2 together, always a plus sign, square the 2, and you have x cubed minus 8 factored. That was a difference of cubes. X squared minus 4 is a difference of squares. The two factors will look exactly the same, except one gets a plus and one gets a minus in between. And you can just think about it as find the square roots. That's what will give you the two terms. Square root of x squared is x, so first terms are x. Square root of 4 is 2. Remember, it needs to change into a multiplication problem. That means x cubed plus 8 goes up to the numerator, and x squared plus 2x plus 4 goes down to the denominator. X cubed plus 8, we can do this. This is almost like what we just got done doing for a difference of cubes, except we have a plus sign. So I bet we're dealing with the cubed root of x cubed being just an x yet. Keep the plus sign, and the cubed root of 8 is still going to be a 2. So see the difference? X minus 2 changes to x plus 2. Square the x, change the plus to a minus, multiply x and 2 together, always a plus in front of the last term, square the 2, and it's so close to what you already had from the first numerator. Very, very close for a sum and difference of cubes. X squared plus 2x plus 4, I want to try to factor it, but coming up with two numbers that multiply to give me 4 and add to give me 2, sorry, there's no two numbers out there to do that. But if you take a look at another part of your numerator, I bet we get to do some simplifying. I'm ready to do some simplifying. We're so close to being done with everything here. So let's see what we can get rid of. I can see an x minus 2 in the top and the bottom. And I can see an x squared plus 2x plus 4. And I can see an x plus 2. Wow, we got rid of a lot, but we have one big thing left, and that is that one trinomial left in that numerator. Final answer, x squared minus 2x plus 4. Woo! Okay, this is it. Here's the last one. Subtracting, and we don't have common denominators. So you have to get a least common denominator, an LCD. LCD really comes from, unless there's factoring you can do to these denominators to begin with, the LCD typically is going to just come from multiplying those denominators together. X minus 3 is completely different than 3x plus 4, and there's nothing I can do to factor either one of those to try to get any rewriting done that will allow me to see some common pieces. You're just going to multiply them together. So here we go. This is the last example. And I'm just going to try to write down what we originally had. Okay, there's your original problem. Common denominator, x minus 3 times 3x plus 4. I'm going to make sure that each of the denominators have those two pieces a part of them. So that's how I build my common denominator. But whatever I had to multiply the original denominator by to get the common denominator, I have to multiply the numerator by that same piece. That's why I was using a different color there. So I have to multiply the first numerator by 3x plus 4 and the second numerator by x minus 3. Sometimes I think you have to play a little cautious here. If I change that minus sign in between to a plus sign, it just moves that minus sign so it's in front of the 2. Then I probably have less opportunities to mess up on things. Now, I'm never going to expand the denominators. I'm going to leave the two denominators as x minus 3, 3x plus 4. And I might as well write both of them down. This is the last time there'll be two separate fractions. I'm going to distribute the x through the 3x plus 4. So x times 3x, x times 4. That should give me 3x squared plus 4x. Negative 2 times x and negative 2 times 3. That gives me negative 2x plus 6. Okay. Leave your common denominator. That will be your denominator for the final answer unless something can cancel between top and bottom. Combine your two numerators. The only x cubed or x squared term is 3x squared. There isn't even an x cubed term. Two x terms. Let's get my powers right. 2x terms, 4x and negative 2x combined to give me a 2x. And one constant term. Okay, so when I look at that, 3x squared plus 2x plus 6, even looking at factoring, if there's any way of simplifying this any further, I know that simplifying further would be making the numerator factor so that either x minus 3 or 3x plus 4 would be a factor. Well, there's a few things I know that this is just not going to simplify any further, and I'm going to give you those few facts and then say, hey, I know we're just leaving it as it is. X minus 3, that minus sign, with two pluses in the numerator's trinomial, there's no way that it would factor with the minus sign. So I know that we could never cancel out x minus 3. 3x plus 4. I know that 3x would be a possibility for one of the first terms in factored form for that numerator. So I like that so far. But a plus 4, in order to have a plus 4, 4 would have to be a factor of that 6. 4 is not a factor of the 6. There's no way that you could come up with 3x plus 4 as a factor of the numerator with 6 being your constant term. So I'm not even going to try to factor the numerator because I know that even if it does factor, it's not going to simplify with the denominator. Call this your simplified answer. And we are done with part 1 video. Thank you for hanging on. Remember, there's so many good pieces to this. Don't be afraid to re-watch things. Your WebAssign has 12 questions to it for Appendix A.4. The last 2 examples are covered in the part 2 video. Don't be afraid to try some optional problems if you're struggling with things, especially on the WebAssign. Take care. Good luck with things. See you soon.